LaTeX or LaTeX can be useful. So most of the graduate students I had, master's or PhD students, wrote their dissertations and papers in LaTeX. Some things are scientific, in Word or something. So, but then extensive equations.
Oh yeah. Like it makes perfect sense. Sometimes it's a little finicky with stuff.
But increasingly people write books in LaTeX.
Yeah.
Right? So, book format, and then different publishers and journals will have a set of templates for use. So you set up things and make it look like a journal. And
A common preamble and all that.
yeah, style files and everything. So there we go. So, right. So today I thought we'd look at some matched pairs, bootstrap. I think it's worth talking about those because there's a little subtle discussion in there about something that they're doing and looking at a couple of the figures in the books that's kind of small to begin with. You kind of have to blow them up. And then it's maybe a little subtle what they're trying to represent. And so it'll be time for you to ask questions about those. I didn't make photocopies, but I'll have them up on the screen so we can look at them. Right? But any questions about things? Anybody have any difficulty getting the data for the homework or going good? Good. Right. So some bootstrap topics. These matched pairs. So the matched pairs data. So we'll have the data we'll have for each for observation I is really the difference between two measurements. The first measurement and a second measurement. It might be before, after, or just repeat measurements of the same thing, or two related variables. For things on counties or companies, it might be one pay period to the next pay period, or one year to the next year, tax year. And so a difference is taken, and the y's generally are associated because they are typically positively correlated. And so can be interested in mu sub d, would be the average difference. And so our estimator d bar would be the sample average. And that's pretty straightforward to, as an estimator, you take the average of the observed differences, and so how do you get a standard error for that, or get a confidence interval for that? And so if we want a 95% confidence interval for the average difference, we could use bootstrap. Right? We could sample within differences. We can resample from those. Sample with replacement n times from our observed differences d1, d2, right up to d sub n. And so our bootstrap sample, we could call it d1 star, d2 star, up to dn star, and we'll take the average of those. Not x bar, we'll call it d bar. D bar star, and if we do that thing, 1,000 to say 10,000 times, and then put them in ascending order, the 200 and what would it be? The 250th, and then we'd have 9,750th in size, right, would give us two cut points, right, and that would define our 95% interval. So I could say we could sort here the d bar stars into ascending order, and then take the 250th and 997. That's really what I mean. Right? And so that's very plausible to do. That's not so much, not so complicated. And so just as a little data example, I have a little data set here about story spoilers. It's people doing rating. Oh, yeah, I already have it open. Nope. Anyway, I read it into R. There's 12 different stories, and then people give it a rating, and smaller ratings were good. And so if a spoiler is given to give away or the story, you get a score, and then the original is scored here. The different stories were scored by different people. So there's multiple measurements. And so the story was presented in a couple different ways. And the difference was taken. Because the same story was done in two different versions, it's matched pairs. Right? And so those are the differences. The average difference, right? What is the average difference of the scores? Well, the average difference was about 0.5, right? Half a point on this scale. Maybe that's meaningful in terms of people's enjoyment and things like that. But if we want to do a bootstrap sample, we can just set up a vector. I'll use it up to 10,000, just like we said. I'll do a little loop. 1, 2, 10,000. Oops. Right. If you're just typing it like that, I'd like to close it off. Right? We're going to sample. Then we can just sample the differences. And there were 12 differences. And we can do it with replacement. So that's our new sample. And we can let our bootstrap sample be the mean, B here, right? Be the mean of those samples. Right? So if we run that, we're resampling the differences, and we get a histogram. We get a histogram to see the picture. It's like that. And the quantile, so if we sort the bootstrap values and take number 250 and number 9750 like that, it will give us those points. I think that will be the same thing as if we do the quantile and tell it to do the 0.025 and 0.975 places. So yeah, it's finding those two places out of 100,000. That's pretty straightforward given everything we've done. So that would be our 95% confidence interval. So it makes some difference. It's not zero. It makes some difference in these ratings. Okay? What if, on the other hand, so let's see. That was this. So D bar. So D bar is equivalent to y bar 2 minus y bar 1. Right? So the algebra, numerically, the average difference is the same as the difference in averages. So conceptually, there's no difference. D bar was the average of these d sub i's. Each of these d sub i's is the difference between two time periods. You can distribute the summation. You can split it there. So you're going to have sum of yi2. Algebraically, that works. So this is y bar 2 minus y bar 1. Right? So whether you view it as an average difference or a difference of averages, it doesn't matter for this one. How about the median, though? You might be interested in a different statistic. What's the median difference? If we're interested in the median difference, we don't have to do that much modification. Right? How about median difference? So to calculate this would mean take the differences and then report the differences, so we get our DIs. And then we would report the median of d1, d2, up to d sub n. And that would estimate the median difference. We can bootstrap that pretty much the same way. Right? Bootstrap for this is it's essentially the same. Right? We can bootstrap the differences, and instead of computing the mean, just report the median. So in this case, the median of the differences was 0.5. And if we wanted to bootstrap that, we could use this line again. And we could use the same sampling statement. But then we could report instead of that as just the median of those differences. And that will give us a sample. Let's see what that looks like though. All right, so it looks a little bit less smooth. I mean, it's a little more chunky. The median, right, is between, since it's 12, right, it's between number 6 and 7, if you assume it, right? So it critically matters with those 2 or 3 observations, you know, the couple, which are the middle 2 that you have in there, right? So it kind of bounces back and forth, whereas, you know, it doesn't matter so much what's on the outer tails. Right? The average, though, as you get different samples, there's a bigger range of values. It's more smooth. Right? So yes, this does give us that. We can look at a confidence interval for the median. There's certainly nothing wrong with calculating that, you know, 0.2 to 0.75. But the sampling distribution doesn't look quite as smooth. Right? So the bootstrap can be done for this. You know, it works better if there's a large sample size originally, right? Because then you have more micro little movements along there, and you see a little bit smoother distribution. One thing that the book will talk about in a later chapter is that with things like with medians or percentiles that kind of bounce from one point to the next and are not quite as smooth functions of the data, like a mean is, right? Then the bootstrap doesn't work quite as well. So there's modifications. There's more smooth bootstraps, there's more things when you estimate a cumulative function and then interpolate in there a little bit more. So there's some advanced methods that work on that. But the bootstrap by itself, how you would set it up for the median of differences, is not really any more complicated. What about, though, what if you were interested in the difference in medians? So what would that mean? You take the median, say, at time 2, right, minus the median at time 1. So these are the medians of the yi2s, right? And this is the median of the yi1. Right? Now, it's not the case that the difference in medians is the same as the median of the differences. It can be that they don't exactly add up. There's not an equation like the other one with the average of the differences or the difference of the averages that makes them equate. Right? So in this particular case, right, so the mean, the spoiler and original were the original 2 columns. So the mean of the spoiler and the mean of the original, and that's a difference of 0.49, and that's the mean of the differences. So the means have that relationship. The median of the spoilers and the median of the originals was 6.89 and 6.1. So that difference is 7.75. So it's not the difference of the median. Right? So you got to do something else. Right? You can't use that same simple bootstrap of the differences to come up with an estimate of this other quantity. Right? So it's a little subtle, right? That's in there. So to get at this, we can't bootstrap the d sub i's to look at this. We need to do it in a slightly different way. Right? To calculate these two things, the median at time 2 and the median at time 1, is we need the y's at time 1 and time 2. So could we take one bootstrap sample of the yi2s and one bootstrap sample of the yi1s as if they were independent samples?
No, because we're doing, aren't they, it's linked
matched
data.
pairs, right? So how could you bootstrap the data some way so that you preserve the matching structure and you see the original y2s and y1s? So we need to bootstrap so that we see y2, y1, and data values are still paired. Because if we get another random sample where we saw the y2, y1s, we can get the median over here, and take the difference. And that would be like our other estimate, this 0.75 number. Right? Any thoughts or suggestions about? So we need to resample from our data somehow. We have two variables, but the two variables are attached to one person. Yes?
Does this have to do with like using a ratio of the two variables? Or would that not?
So the ratio would kind of be the similar issue. If you took the ratio before, right, and then bootstrap ratios, that could be used as a, if you wanted to, if the estimator was going to be kind of an average ratio.
Yeah.
Right? Then you could bootstrap, you could compute ratios before and bootstrap those. But in this case, we actually need all the y's
Yeah,
in
so
both
that
of
would
those. So.
help.
But it's in addition to median, like a ratio, if y1 was one type of expenditure and y2 was another type of expenditure, you wanted that ratio. So everybody has a personal ratio. And you wanted the average of the ratios. You could bootstrap ratios. So one way we programmed that at one time, right? Like for the two sample one, it was a little more convenient to bootstrap or sample indices. Right? So we could resample people, right? And then each person has two measurements attached to it. Right? So a way to do that is to sample n times with replacement from the numbers 1 to up to n. And then our sample is yi1, yi2 pairs for selected row numbers. So we're going to pick n people, and we're going to keep there. So we could get their paired measurement. Some of them will be copied over 2 times, 3 times. Others will be omitted. Right? So we'll get that's the sample, and then we compute from that sample the median of the y2s. Oops. The y2s minus the median of the y1s. Right? And so doing that one time gives us one value of this difference of median. If we do that 1,000 times, we get 1,000. So it seems like just a little subtle change, right? But it changes kind of the structure of how we do the bootstrap. We need the y2s, y1s, but we've got to keep the pairing. And so more advanced theory and applications of bootstrap often face that, right? So you have a time series of data, so there's some time structure. You just can't bootstrap individual observations and ignore that. It's going to mess things up. Right? So it can get, or if you have the geographical area structure, you can't just bootstrap without respect to the design and all these other things. So it can get more complicated.
Because you need your resampling to be independent.
Yeah, if you need it independent, you need it to match the overall data structure like the matched pairs. Right? So how would you program that in this case? It's not a whole lot different. Right? We can reuse this. Right? And I'll copy this code and eventually put it on the internet so if you want to look back at it. So now we're going to sample numbers 1 through 12. Right? 12 times and with replacement equals true. And now our bootstrap estimate, we're going to do the median of the spoilers, right, of that sample, right, minus the median of the original with that sample. Right? And now my S there are numbers 1 through 12, so they're row index numbers. And that gives us this histogram with the bootstrap. Again, it's a little chunky. It's dealing with medians. But the interval that it comes up with is 0.2 to 0.1. So it's a little more variable than the means in terms of if it's spread, but that reflects the slightly difference, right? So this point about this, this little thing is contained. So in 5.4.1 in this section on matched pairs.
They did the divers.
Huh?
They did the divers.
They did the divers there. It's also a small sample size, but there's a remark on page 126 that talks about this. So there's just a couple paragraphs, and contained in that little paragraph really is trying to get at this distinction, right? But it shows that you do the bootstrap, often have to consider the data structure, and sometimes we'll consider what model you're estimating, to make sure you have the data. And it's very flexible. You can bootstrap individuals. If there's only one variable, you think about just bootstrapping the variable, but really we're kind of reproducing the data structure right in there. But any questions? All right, well I wanted to look, again, I'll after class grab that code and put it up so it's, you can look at that again. I'll save that after class, right? There were a couple of, where are you? Graphs in there. Let's see, I'll go to, oh, there's a binomial illustration. The copies of the figure. There's the contour. So this is a figure 5.19. About the median, and it's kind of even small there. So let me see if I can get my figure size control. So in this, it's talking about variability in bootstrap distributions. It's what it's trying to illustrate. So here's a population, and here's the median. And it gives examples of different samples. So sample 1, sample 2, sample 3, sample 4. Sample 5 as example. I don't know why that one's, maybe they use a lighter color, and copying it didn't come through as well. Right? So those are the actual sample points there, right? And they generally kind of match that distribution in a way. This one particularly has a concentration here and there. The other ones don't look quite as distinct. And the sample median is here. So you have sample medians kind of moving around the actual population median. I kind of like this idea of capital M, lower M. Maybe I'll start doing that right there, right? And there's only n equals 15. So they work out that the actual sampling distribution would look like this, right? Right. So if you could take thousands and thousands of samples of size 15 from this, the median distribution would look like that. Right? So it'd be more smooth, right? Because you would get thousands of samples, and there's tons and tons of different possible values you could get here. So you'd get a nice, smooth sampling distribution. But a bootstrap tries to use these data through resampling to reproduce this. And it has a hard time with the median. The mean works out just fine, right? Because the average it has 15, 12, 15 choosing with replacement is there's 15 to the 15th different possible samples, and there's a great deal of,
Gross.
it's a lot, yeah. So but the median depends on what's really concentrating at the middle, so it kind of bounces around between these few points here, right? Because if you leave that middle one out, right, maybe that's that's just the median, it's a little bit taller. But if you leave one of these out, then it jumps to the next one, and so on. So it can't reproduce it so well, right? But what we'll talk about toward the end of the class, right, is you can do the bootstrap, but do kind of smoothed ones. So you can make them smoother. And sometimes this particular sample ended up being quite split, so even the smooth bootstrap sample makes it kind of look bimodal. It could be over here, or it could be over here. The other data sets are not quite as spread, and this one in particular seems to be more concentrated in the middle, so it's just, so anyway, there's techniques for smoothing the bootstrap to do it for other things. Right? The goal is really the same. You want to know what's the sampling distribution of your statistic. Where are the likely values of the median in this case, given your data and the simulation. So there's enhanced ways to do that, and that's what this picture is trying to illustrate. Right? But I thought it was kind of small. It was only a few sentences, a few half sentences to try to describe what's there, but that's what it's trying to show. That the bootstrap can have problems. If you have small sample sizes, you're trying to do the median, or a percentile that will, like the 50, the fifth percentile, right? That would jump from one value to the next, depending on one or another values being in or out. The second graph that's after that is this one. Right? The bootstrap is influenced by the shape of the data. Right? So this was another illustration here. So this is an exponential distribution, right? So the data is all positive. Here's some sample histograms of data, different ones. That sample data over here, n equals 50, follows that general decreasing curve pretty closely, right? Looks like it gets a few big ones out there every once in a while, or more concentrated over here. And now it's the sampling distribution for x bar. So if you really could take thousands of samples of size 50, the sampling distribution would look like this. It would be centered at mu, right? And it would be 50 is pretty good size for central limit theorem, so it looks pretty normal. But the bootstrap gets based on our sample data. So if this is our sample data, and we resample from that, right, if our original data ended up being a little bit low, right, then our sampling distribution ends up being a little bit lower. Right? If our data ended up being a little more concentrated, then our sampling distribution ends up being more concentrated, because we're simulating from our data to try and mimic that process. On some of these other ones, they kind of arranged it so that the mean is increasing there, and then this one's out here. And so the sampling distribution that we simulate kind of matches that. Right? But the book talks about bias. There's a difference between our x bar and where the bootstrap distribution seems to be, right? Because if there's simulation skewness in our data, it affects both our data and then our bootstrap, right? So there's ways to put that together. So there's modifications that do a little bit better job with bootstrap, and that's kind of what they're showing over here. So again, this is more in chapter 7, so in a couple chapters we'll see kind of a modification that works better for testing purposes. Right? So we don't need to do that right now, but in this part that's talking about other aspects of bootstrap. It's kind of pointing in the direction that, yes, we'll do things a little bit more advanced, a little more sensitive to get better estimates. Right? So the goal is still the same. We want to know what the population average is in this case. We have a sample estimate and we want an interval based on that. Right? And so the bootstrap, just doing a simple bootstrap, we can already detect that things are going to be a little bit less than perfect, and then people have figured out ways to do some adjustments. So we'll start with exactly what we've been doing so far, and then in time build up a little bit more sophisticated alternatives. So. But anyway, those seem like kind of dense graphs, little hard to read what was going on there. So I thought it would be interesting to talk about them to kind of finish up this part. So, but any questions about? So, right. And we will explain we'll figure out how they get that, in a little bit later. So what the plan is kind of for this second half of today, the second part, right, is we're going to start looking at, in the course, in chapter 6, the general title is Maximum Likelihood Estimation. And so now we're going to look at this and then a couple other procedures. Well, how do you come up with estimators in more complex situations? How do you choose among different estimators in terms of how well they work, right? So, so maximum likelihood estimation, right, is a procedure for generating estimators. So statistics that we would use to estimate a parameter. From probability models. And so what I wanted to look at today with the handout, does everybody have a copy of the handout, I think? Yes, you do. Is just kind of give a little glimpse of comparing estimators, that you can do different estimators for some things. And then eventually we're going to figure out how to compare them and figure out how did we come up with that in any case, right? And so we won't do really too much with maximum likelihood. Today we might put up one or two equations at the end. The more it's about comparing estimators. So the first example, right, is a genetic illustration. So let's say that there's genes that come from a parent, and it's either big A or little a, like a dominant big A and a small a recessive. And let's say 40% of the population has this, and 60% of the population has this, and so that a contribution from a randomly selected mother could be one of these two. And then a father would also contribute one of these alleles, right? And depending on the outcome, you could get a big A, little a combined from the two parents, or a big A, little a. I said, well, two big A's, big A, little a, and then or two little A's. They could happen like this, right? And so this, if they're independent from mother and father, the chance that you would have two copies of the big A, assuming they're distributed this way equally, equal chances, same chances in males and females in the population. But you get a 40% from the mother and a 40% from the father, so about 16% of the cases would be in that category. Right? For the ones that are little a, about 60% of the time a mother would contribute that, and then 60% time a father would contribute this, so that's about 36%. Now, ultimately, we won't care if it's big A, little a, or little a, big A. Kind of together, you have one of each, so we think it functions generally the same. So if it's this little a, then that's from the mother and then the father, or it could be reversed, where the mother and father's contribution switch. So the probability of that is 0.24, 0.48, right? So with 16%, we're going to see double A. 48%, we're going to see this heterozygous situation, or 30%, we'll see the double recessive. Right? So that's fine. That's from probability, fairly simple Mendelian genetics, right? Of this, right? So, but let's say that we have data. So suppose instead of having these known numbers, we can say there's a certain probability that we're going to get a big A. Right? And 1 minus p is a certain probability we're going to get the little a, right? In the population, right? And so, but p is unknown. We don't know what the rates are in the general population. So we gather data. So let's get 100 individuals. And so we're going to get a certain number of cases. I'll put this on the next page. So let's say that we got little a, big A. And for the time being, we're going to say that I made a little table here on the handout. I generated random binomials that have only a count of 1, so they're either 1 or 0. Big A means 1. And little a means, 0 means little a. And so the crosstab there has 24, 21, 31, and 24. So if we translate this into the information, big A, we had 21 out of 100. Big A, or little a, big A combined. These big A, little a, these two actually ended up being 48, which is kind of what would be predicted. And the little a was 31. And so if A occurs with probability P and little a occurs with probability 1 minus P, the chance of 2 copies of the big one, if they're independent, P probability for first, P probability for second is P squared. The chance for 2 small ones is 1 minus P squared. And the chance for a heterozygous of either type, well, there'd be one big A, one little a, so it would be P times 1 minus P, and it could be reversed, right? For those, right? So those are the probabilities based on an unknown P. So now our question is, what is P? From this data side, what is P? How could you use these data to estimate P? So what would be one suggestion?
We could do
Is it as simple as taking the square root
of one of these things, right? So like here's P squared, right? P squared is supposed to be like this number. So, because this is get the chance of getting 2 double A's, and we have 21 people out of 100. Right? So 21 100s are supposed to happen P squared. So one estimator, I'll just put a little hat over it. We could take our 21 out of 100 and take the square root of that. If that's our estimator, we get 0.458 right, as the estimate. I generated the data with 0.4, so that's not too bad, right? But is there any other alternative? And this it's kind of encoded in there on that. Right?
Yeah, you do the
Right. So this one also has a p in it, right? You take the square root of that, you're down to 1 minus p.
And take the average.
You take 1 minus those. Well, yeah, so you can do other things. A different alternative. You could take the 1 minus 31 over 100. Well, no, take that square root of that. Sorry.
Yeah.
You can take the square root of this thing, right? Because that's going to be kind of like estimating the 1 minus p, and then take 1 minus that. So that would be a different possibility. That ends up being 0.443. So it's different. Yeah, maybe you could take the average of those two. That would be a compromise. The one that's stated there has 21, well, 2 times 21 plus 48. So there's 100 people, but there's 200 genes, right? If the genes randomly associate in the population, it's kind of like a sample size of 200. So this one really counts as 2. So, a different option is to take 2 times 21, plus there's 48 cases, 24 and 24. We only get 1 p. And then divide by 200. And that ends up being 0.45. Right? So I have 3 different options. Right? That gives slightly different estimates. And so the kind of territory of mathematics statistics is thinking about which one of these is the best. Is one more desirable than the others? And what rationale could you have for choosing among those?
How can you say something is the best if you don't have the actual information to compare it versus? Like in this, you generated it with a 0.4 probability.
Right, so you know which one's closest in this case.
Exactly, but in like a general scenario in which you didn't know the probability, how could you?
Well, right, so if you didn't know p exactly, but say I'm in a class of problems where I think it's about 0.4, right? I could do this simulation, 100,000 times, and see how many times, among these 3 or other things, which one's closest, right? Which one gets closest the most number of times, which one has the smallest error on average versus that. Right? So I could choose among these different things, right? But that's only when p is 0.4, right? Maybe p.2, a different one would win, right? Because the shape of the binomial sampling distribution changes as you get different values of p, right? So you can simulate a few cases, and that helps, right? So it's good to have a theory or rationale, right? So the other thing that could happen is in probability theory. We have these different estimators. So under a binomial model with a general p, we could look at the expected value of these things. This one is unbiased. These two are slightly biased. You could look at the variance of these things, and there's a measure called mean square error that's variance plus bias squared, so it kind of trades off the two. Right? This one also, this one only uses one cell. It doesn't really use the other cells. This one also just really uses one cell, and it uses kind of one cell and the things that are not in that cell. This one at least is using 2 of the, well actually 3 of the cells, right, because it's 21, and using those 2. So that in some sense might be using more information. So some things will just obviously, looking at it, it seems to be, if you had, that's one issue with the ranks for some non-parametric things, or just, using part of the data, right, just not using as much information. So maximum likelihood, right, in a likelihood function, is a probability density function. I'll just say probability function for now, since we're dealing with discrete things, right, with the parameters viewed as unknown. The parameters viewed as unknown and data values viewed as known. Right? So if we had 3 cells here, P1, P2, P3, that add up to 1, and we have our data, our counts, x1, x2, x3. These things add up to 1. These things add up to n. Right? They're the likelihood function for our parameters here, P3. Well, with a certain probability, we get a count in this cell. We get that genetic response. And how many times does it happen? It happens x1 times. And a certain number of times we get a response in this cell, and it happens with that probability. So there's a P2 to an x2 and P3 to an x3. In our actual problem, these things have a little more definition. Instead of it just being P1, it was P squared. So the likely function really has a P, and then it's squared 2 times x1. At the second one, P2, the probability of being in that cell was really 2 times P times 1 minus P. So if you put that there, 2P, 1 minus P, all of that to the x2. And the P3 in this example was 1 minus P squared. So 1 minus P squared to the x3, you can write it like this. That's so when we see our data, I know the counts of x1, x2, and x3. And maximal likelihood says to find the values of P through this function that makes the data as likely as possible. So anyway, find a value of P that maximizes that. Right? And that's what we're going to do. Find P to maximize this function. And the maximizer value is called the maximum likelihood estimate. So P hat, maybe with a little MLE, for the maximum likelihood estimate. So it's going to give us a direction, right? An objective function from the probability distribution that we can maximize, and that's going to give us our functional form for estimation. Right? And we'll actually go through this is where we start using calculus, right? Because we want to maximize this, so rearrange terms a little bit, do logs, take derivatives, set it equal to 0, something like that. So we're going to get a different estimator, and then we'll want to talk about is that a good one or not. And there's some desirable properties about it, and that's why we're going to talk about it. But it comes out of the probability model, and then we do that work. Right? So we'll do that on Wednesday. We'll go through the calculations, but that's kind of setting it up. The second kind of illustration of this on the handout, I put those on here if I can get back to them. I don't know where those things are hanging out. Oh, there it is. So there's a famous data set. The Prussian army had units, horses, pulling things around, doing exercises with a lot of people, going around fast, and there'd be accidents. They work with a lot of horses, people get stepped on by horses, bitten by horses, and sometimes killed by horses. Right? They just get kicked, or a horse falls down. This is a military unit, so there could be explosions and other things going on. Horse falls on somebody, or maybe they get killed by that. But this is horse kick, so they fall off a horse, get behind a horse or something. So accidents happen. They would happen on a farm with horses anyway, but this is kind of extreme circumstances. And I don't know the total size of a unit. Is that 100 people? over is this a year's time or something like that? But so it happened. If that has a Poisson distribution, that kind of models something that happens occasionally. If you get 10 units, you say the average number of deaths would be 6.1. And so I generated 20 observations from a Poisson random variable with that rate, lambda. So our parameter is called lambda. And it really is 6.1, and that's what we would like to do. Right? So how do we want to estimate that? Well, we could take the mean of these variables and we get 5.5, 5.45. On the face of it, that looks like not too far away. Right? A little bit lower in this random sample of 20. The median was 5, but the mean can be affected by outliers, so if you kind of do a trimmed mean, maybe you take off the last, the smallest and the biggest observation. So this sorts, these kick deaths sorts these numbers from smallest to biggest. And then I drop, it's only the 2nd through the 19th. So it's dropping the smallest. So it must drop 2, and then it drops the biggest. So it drops 2 and 10. Now those are not particularly outlying, so I wouldn't necessarily think you would need to do that in this case, but that's the idea of a trim mean. If one of these had been 25, it would really be sticking out there, right? And 25 would pull the mean up. So maybe we would drop the biggest. And it's a very small effect, makes it 3.40. Right? So those are different estimators, and maybe we'd want to pick one of those or something different. Right? We want to come up with a rationale for deciding which one do we want to use. The impact that the change in parameters have are, if you have a different parameter value, you get different outcomes, different probabilities. Right? So these things, so the density of Poisson gives us the probabilities. So say you take a new unit. What's the chance? I guess 10 more units. You take another group of 10 units. Maybe that's a company or some other name. Right? What's the chance you get 0 deaths in that new company of 10? Right? Well, if lambda is 5, here's 5, it would be 0.7%. If it's 5.4, it would be 0.5%. If it's 5.5, it would be 0.4%. So it's going to change the probabilities that we get for different outcomes. And so this is the probabilities of 0 through 12, and 0 through 12, and 0 through 12. So something like, what's the chance that we get 6 deaths? If it's 5, the probability is 0.146. But if it's 5.4, it goes up, and then it goes up again, right, to that. So it changes the probabilities, right? So knowing, that's why we care about these parameters, in a model, because it affects the different chances and things that we're going to see. Right? So which one of these things do we want to look at? Right? So in this second example, it's a Poisson distribution. Lambda is the rate. It's a parameter, we could call it a rate parameter. And lambda generally is unknown. Right? How do you estimate? Estimate lambda. Well, if we have a sample of data points, independent sample from this distribution x1, x2, right up to xn, we could look at x bar, we could look at the median of the x's, and then that other thing, would be a trimmed mean. So, those are kind of the examples of different estimators. Which ones are good? Right? If we had a value of lambda in mind, right, we might simulate 10,000 different samples, right, or 100,000 different samples, and see, does one of these estimators get closer on average to our 0.61, if that's what we're using for simulation, or 6.1. Right? So in individual cases, we might do simulation. There'd also be some probability that we'll do to try to evaluate them. But a general way to come up with a solution is maximum likelihood. So a Poisson probability probability that a Poisson random variable equals some value is lambda to the k e to the negative lambda over k factorial. Where the k factorial is this thing for combinatorics. That means k times k minus 1 times k minus 2, right, all the way down to 1. And 0 factorial is 1. But that's the probability for one measurement, right? The probability, right, of those. And so these are the probabilities that are illustrated in that chart. These are the probabilities that come, probability of 0, probability of 1. These are those things calculated with different lambdas that are in there. But if we have a sample of size n, I'm going to put an I on here. Maybe an I there. It's a little bit messier, but that's the factorial, so I'll make that a little bit bigger. So we have each observation has a probability structure, a probability based on its outcome based on that involves lambda. So if we have n independent observations, n independent Poisson lambda observations, the likelihood is the probability that x1 is x1, x2, well, I guess I'll keep it as k, but written it once as k, I'll write it again. K1 that x2 equals k2, that our nth value is kn, right, like this. They're independent, so actually it's a product of probabilities. A joint probability of all n outcomes together becomes the product of those. Right? And so for each one, we can put in that Poisson probability. We're going to get a product going from 1 up to n. So lambda to the ki, e to the negative lambda over ki factorial. And so the process of maximum likelihood would be taking this function. Right? K's are numbers that we see. Right? There's a number of kicks. Right? So we know those. We want to choose the value of lambda that makes our data as likely as possible. So we want to maximize this function as a function of lambda. So for maximum likelihood estimation, find lambda to maximize the likelihood function. And so that will give us a formula, a way of doing estimation. Sometimes the maximum likelihood estimators, a lot of cases that we'll do, end up just in a closed, what's called a closed form expression. It's just an expression that we can just calculate. Give me the numbers, and here's the way I calculate it, like I would calculate the mean or median or something like that. Sometimes it's not necessarily a closed form solution. Maybe sometimes there's a series of equations you have to solve, right? But it will use calculus. We'll do things combining terms. We'll take some logs, take some differentiating, and so it's for most of the things that we'll do, it's just taking a derivative with respect to one thing at a time. But that becomes the method, right? The method of maximum likelihood to find the estimator. And we'll do other things to explore how well that does. But yeah, so we'll come back on Wednesday and compute through a couple of these cases and see how they work out and what estimators they come up with.
Number 2 for abstract, I guess the power set. Well, I mean, I did it in a way that was definitely not complete, but
Thank you.
That's the first time we've ever
have a
met.
good one. Well, for me, what helped is remembering that the symmetric is the same as XOR.
Pretty good.
How's tutoring going?
Pretty good, not too bad.
Yeah.
I just pretty much just sat in the classrooms on like Fridays because it's so early in the semester that no one's really showed up. I forgot. Thank you for recommending me for that.
Oh, sure. I'm glad that, it's valuable to see somebody else's presentation. He's
Yeah.
doing some different things.
Yeah, it's definitely different than how you taught last semester, but it's interesting.
Yeah, so good.
Fun.
Okay.
Have a good day.
So you had to prove that it's an operation.
Yeah, it's an operation.
Yeah.
So how do you do that?